Hello again, everyone. So in this video, we'll again be talking about vector spaces, but we're going to sort of take a different route. Before, what we were doing is we had the definition of a vector space. We were given a certain example. So for instance, we had Rn, and then we had to show every axiom. We had to show that every axiom held for those two specific operations. So the vector sum and the scalar multiplication. In this video, we'll be doing a counterexample. That is, I'm going to give you an example of a vector space, and we're going to see why it fails to be a vector space. So my example here is, suppose we have the set R2, right? The set R2 is like Rn, just that it has less components. So we have A1, A2, such that A1, A2 belong to R. So again, my field here is the real vectors, and we define the following operations. The following operations. Okay. So remember, we need vector addition and scalar multiplication. So for vector addition, I'm going to say that A plus B, so A1, A2 plus B1, B2 is equal to, as we might expect, A1 plus B1, A2 plus B2. Okay, so where, of course, A and B belong to R2. Now for scalar multiplication, I'm going to give a twist to my scalar multiplication definition. So I'm going to say, so C belongs to real numbers and A belongs to R2, and I define CA by C times A1, A2 as, let's say, minus CA1, A2. So already it probably seems like this guy is going to cause a problem. Like it doesn't seem like some of the axioms will hold for this definition. So what we want to do in that case is we want to show that this vector space, we can't call it a vector space, that this definition fails to be a vector space. Or I guess this set. So this definition of a set fails to be a vector space. And how we show this is by using a counterexample. So use a counterexample. And a counterexample really is just a fancy name for saying a real example. So an example that contradicts or that goes against, so that contradicts, in this case, one of the axioms that we have, one of the 8 axioms that we have. You might have less, but in either case, it'll fail some of your axioms. Not all of them, it might just fail one, but if it fails one, then your whole definition fails to be a vector space. Okay, so looking at this guy, it probably seems like one of the scalar multiplication axioms is going to be trouble. Okay, so what I mean by that is, take, for example, axiom 5. So if we take axiom 5, axiom 5 says that for all u belonging to V, one scalar multiplied u is equal to u. Now, let's see if this is true. So check for our definition. For our definition of scalar multiplication. Because scalar multiplication varies from one vector space to the other. It's never the same. So for our definition of scalar multiplication, we have this guy, right? So if, according to this definition, we did 1 times, and now I have to use a real concrete example. It can't just be with symbols like A1 or A2. Even though it's tempting to do that, you have to show a real tangible example. Let's say 1 times, I'm going to pick 1 and 2, right? So this should give me 1, 2. But according to the definition I have here, it's actually going to give me minus 1 times 1 and 2, which we know is equal to minus 1, 2. But this guy that I started with on the left, so this is my vector u. This is definitely not equal to this new vector u. Or in this case, I can say u1 and u2. So my left-hand side is not equal to my right-hand side. Hence, what you would say is, hence, axiom 5 fails, and this shows that I should have named, what I should have done is I should have named R2V. So if I say we have V equals R2, so I have a set VR2 where we have these following vector addition definitions and scalar multiplication additions. So I'm just renaming my set with these two operations V. So you would say that this shows that V is not a vector space. Okay, and so you've shown using a counterexample that a particular vector space or supposed vector space is in fact not what you suspect it is because it fails a certain axiom.